Hello. Welcome to Answer Everywhere. Today we're taking another look at some open core stuff. This is some Verilog that describes FPGA thingamajiggies, tools, or tips. Not tips, chips. And this particular hardware is for 1G Ethernet with a deep packet inspection. Hello, Broken Record. You, somebody, was that you with a different name that posted about it yesterday? sklearn is added to the request thing. We're not there yet. It may be at some point in the future. sklearn is an interesting repo. I would be happy to do it. It's just, we're going to go through the standard request process. All right, so I downloaded this repo, which I think is in this trunk folder. And I looked at it a bit yesterday, and I have no idea what this Verilog stuff is doing. We have RTL, which should be the register transfer language. TB and TC, I don't know at all what they could be. MSIM, who knows? Layout, I also don't know. So maybe layout is like drawings. You have process.sh, this is some shell script. Vivado. CLR is maybe clear. This is like kind of like make clean. Perhaps we're just going to make some directory called process and change into it, and then we're calling Vivado. Vivado. So let's see if what Vivado is. Okay, so Vivado is what? Some AMD thing, I guess. Enhancements for designing with AMD Versal adaptive system on chips. I don't know what Versal is either. Vivado for Versal. So let's look up Versal. Versal adaptive SoCs. For any application from cloud to edge. Highly integrated multi-core compute platform that can adapt with evolving and diverse algorithms. Architected around a programmable network on a chip. This is just marketing speak. Let's ask one of the AIs. What is AMD Versal? And what is it, Vivado? So Versal is a line of adaptive SoCs, advanced, highly integrated chips designed for a wide range of applications, including data center, automotive, aerospace, and 5G wireless. So it's heterogeneous. It combines various processing elements, including a traditional FPGA fabric for hardware customization. So there's some FPGA that you can program, some processor subsystem, like ARM processors for software execution. So I guess like a CPU, and specialized engines such as AI engines and DSP engines for accelerated processing. And they come with a bunch of different series, I guess different configurations. And then Vivado Design Suite is a software suite from AMD that's used for the design, development, and implementation of hardware systems on AMD FPGAs and adaptive SoCs. So so AMD has this these kind of like FPGA plus things that have FPGAs plus some other stuff that you might want if you're in this hardware game. And I guess that this project is using that. BD, I'm going to guess, is board. Tickle, I don't know why people are using Tickle, but let's look it up. It's the tool command language, a high-level, general-purpose interpreted dynamic programming language. Very simple but powerful. It casts everything into the mold of a command, even programming assignments like variables. So this, it's not saying functional, but it sounds kind of functional. It's embedded into C applications for rapid prototyping. GUIs and testings. So has this basically been replaced by Lua? I have a C++ server-side project that I need to embed in some blah, 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 blah. They're both very well suited to the task, extremely well. I don't like Lua, and because they like Tickle. I feel like they're probably competing overall for the same space. Tickle seems older. Seems like newer stuff is mostly using Lua. I don't know if that's for any good reason or if it's for only bad reasons. Let's see, Lua's from when? 1993. It's newer by less than a decade, but it seems to have had a resurgence. Okay, so Tickle, I'm going to think of as kind of like Lua. It's something that's typically embedded in C. And what is this? This is vdebug. Oh, look at that. That's unreadable. I do see some stuff like microblaze. That's the name of a chip thing that we learned about yesterday. You can watch the video from yesterday. We've got this get devices thing, filter, set property. I don't know if these are comments or this is uncommented stuff. Okay, at any rate, this doesn't seem like the most productive file to look at. Here's another Tickle project, Tickle file. They're calling open project on whatever this XPR thing is, config web talk with user off, update, compile order, etc. Okay, then V setup. They're going to create a project with this part. I'm guessing this is some chip or FPGA part number. Integrated circuits. For $2,598, DigiKey will sell you one of these things that they don't have in stock. I don't know if that's because they're outdated. It's just this thing. What? It's like an empty, it looks like a pegboard. Wait, go back. But what does it do? It claims to be a field programmable gate array. Let's look at the datasheet. Please wait for your document to be downloaded. Okay, this looks like a C-Links thing. Does AMD own C-Links? What's the relationship here? Yeah, okay, so AMD acquired C-Links in 2022. So this is just some, can I pop this out? This is some FPGA. Okay, that's good enough for me. I'm getting rid of open cores. You go away for now. Keep getting in my way. Okay, so setting these properties like the board part, whatever this means, this is the C-Links, this is the KC705, which is not the same as this, but it's some presumably piece of hardware. Something about default libs, maybe default library. Probably the target language is Verilog. And this is just setting up some properties. This is like a description, I guess, of what the thing is. We're going to add files with no recursion, whatever SDC file is, some project files with some SDC format. And then microblaze design. Microblaze is like an AMD, I think they call it a soft processor or a soft CPU. That is like a software CPU type thing that you can add to your AMD FPGA stuff. And then whatever SDC is, unused pin, pool none, set property, blah, 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 blah. Let's look up what SDC is in XDC. In fact, let's just hand these off to Gemini, because I think I'm going to have a hard time Googling those extensions. Okay. SDC is synopsis design constraints. This is a standard format for specifying timing constraints. It defines things like clock frequencies, clock relationships, input-output delays, and timing exceptions. The Z-Link AMD project's SDC files guide the synthesis and implementation tools to meet the desired timing performance. So these are, we looked a little bit about, maybe last week, I think it was, at how the like Verilog is synthesized essentially using a constraint solver into a layout and or into a description of the gates, and then those gates are laid out. This seems to be part of just specifying in a simple format what some of the constraints are to drive the constraint solver. At least that's how I'm going to think about this. I don't know what B, P, and T are. Maybe Gemini will tell us that. So I'll ask if there are any common naming conventions, or is this probably project specific? Okay. This seems like there's some conventions. I'll like peek at one of these. Can I open these all at the same time? We have IO standard LVC CMOS. 15 get ports LED 8 bits try O. Package pin. Okay. I'll just say, tell me about some of this. Here, just the gist. I don't need full details. I'm just trying to get flavor. Oh, whoops. Did I paste it or did I not paste it? Gemini makes it hard to see, because I frequently forget to paste. And then Gemini makes it hard to see if I actually did. So these are the Z-Link's design constraints. They have pin assignment and standard IO functions. It's assigning specific FPGA pins like lock or package pin to various signals in the design. Okay, so I guess these package pins are like hardware stuff that is designed by the FPGA creators in the FPGA factory. These are in the hardware world, and then the signals in the design are in like the software world. This is like in Plato's cave. These are inside the cave, and this stuff is outside the cave. And this is kind of like wiring up the inside the cave stuff to the outside the cave stuff. It also has electrical characteristics like IO standard for those pins. I guess that makes sense. So we're to physically connect the signals and how to handle the electrical signals. And we have clock reset LEDs and so on. UART, I forget what that is. Is that for debugging? We'll look it up in a second. Input, output, in essence, blah, blah, blah. Okay, great. We'll look up UART. Universal Synchronous Receiver Transmitter is a hardware protocol that allows devices to communicate by exchanging serial data. We have two wires to transmit and receive data. It has a ground connection at both ends. Uses a packet mode of transmission. A packet includes a start bit, a data frame, a parity bit. A packet has a start bit A bit? How do we know? I guess this is organized into bytes or something, right? There's a start. I don't know why you need a bit for that. A data frame, a parity bit, and stop bits. That's confusing enough to logic low. Oh, okay. Well, hang on. So there's 5 elements. There's idle, which is a logical high, which I guess means there's current. And then when we are about to start, I guess idle is high, probably to, it's just totally guessing. I have no idea what I'm talking about. But I'm going to guess logical high is on, just to prevent you from confusing a bad or damaged board or non-functioning board with one that's idle. So if you're going to communicate that you're ready and waiting, you have to send a 1. Essentially, then when you're going to start, you're going to dip down and send a 0. And then after you've dipped down, you have 5 or 9 bits to represent a character, and then you have a parity bit, which is probably just there for like a simple error correction. And a stop is another high. And how do you know which thing is a bit? I guess that depends on the clock, right? Because you're going to sample at some rate. All operations of the UART hardware are controlled by an internal clock signal, which runs at a multiple of the data rate, typically 8 or 16 times the bit rate. So 8 or 16 times the bit rate. So I guess if you're going to send a bit, let's have like a really slow GPU that sends a bit once per second. Then the clock is going to, I guess, oscillate 16 times a second so that you're way oversampling and you're really sure what a bit is, I guess. And also maybe because to produce a bit, you need to do some computation that might take 16 clock cycles to do. Okay, let's ask the AIs if this is right. The receiver tests the state of the incoming signal on each clock pulse, looking for the beginning of the start bit. If the apparent start bit lasts at least 1/2 of the bit time, it is valid. Okay, so you don't have to last the full bit time. You just have to last more than half? I don't know. I'll read this, and then I'll know more. But that sounds like kind of what's going on. I'll assume that's the case. Let's go back to the files. Okay, so we have these descriptions. XDC, is that where we just were? How about this physical timing thing? We've got this triple bang. I don't know what this means. Set reacts, receive, clock, var, get clocks, dash of, get ports, etc. The RGMII receive interface requirement allows a 1 nanosecond setup and 1 nanosecond hold. This is met, but only just so constraints are relaxed. We looked up RGMII before, but I forget what it was. Reduced gigabit media independent interface. The reduced gigabit media independent interface uses half the number of data pins as are used in the GMII interface. What? Why are you starting down here? Oh, okay, so the R stands for reduced, but here's the non-reduced version. It was originally defined as a standard interface to connect a fast Ethernet, that is 100 megabits per second, medium access control, block to a PHY chip. These are all things that I've heard, but I'll read about all of these. Network data on the interface is framed using the IEEE Ethernet standard. As such, it consists of a preamble. So this is just Ethernet stuff. There's a CRC, aka cyclic redundancy check, which is kind of like a checksum. Is it technically a checksum? I'm not sure. And I guess this thing is doing what? What is it doing though? Maybe I want a different source. Is specification for connecting the MAC and PHY of an Ethernet interface. So I need to know what MAC and PHY are. Tell me about this thing, MAC and PHY. Okay, as is reasonable, PHY is the physical layer. I guess. I don't know why it's all uppercase. It's the physical part of Ethernet. It is responsible for the actual transmission and reception of electrical signals over the network cable. It handles things like signal encoding and decoding, converting digital data into analog signals and vice versa, interfacing with the physical medium, for example, copper or fiber optic, and auto negotiation, determining the link speed in duplex mode. And then the MAC is the media access control. Is a sublayer of the data link layer, responsible for, okay, so MAC addresses, framing, packaging into Ethernet frames, error detection, and controlling access to the network medium. It handles the data side of Ethernet. So the RGMII connects the MAC and the PHY. It's standard that defines how the MAC and PHY communicate with each other. So the PHY is going to take, I guess, the high and low signals from the wire. It's going to have some clock and turn those from electrical signals into bits, I think. And it will take those bits and hand them off to the MAC, and the MAC will somehow interpret them as things like frames. And may also like detect if the physical layer is handing it nonsense, perhaps. It reduces the number of signals compared to older stuff, and it's used for gigabit Ethernet connections. Okay, so the MAC receives data from higher level layers of the network stack. It adds addressing and control information and creates Ethernet frames. It then sends the frames to the PHY through the RGM to II interface. Okay, so now with that, we can maybe look at like what actually. So this is telling me that it's an error correcting code. Was that my question? I forget what exactly my question was. All right. So here's some description of the RGMII thing. So we've got some bit values, and they tell you things like what we're capable of, like unidirection, auto negotiation, whether we've established a link, and then we've got some transmitter signals. TX clock, transmit clock direction is from the physical layer to the MAC. And then we can transmit data bit 0 from the MAC to the physical layer. Everything else seems to be from the MAC to the physical layer. And then receiver signals. Okay, that makes sense because I guess what it means by transmitter signals is we are sending data onto the card. So the data is coming from the application, ultimately down to MAC, and needs to be physicalized. And then when you're receiving data, the physical layer gives you the clock again, and then you can receive a bit 0, 1, 2, or 3. And some stuff about whether the data is valid, whether there's an error. Carrier sense, I think, is detecting whether somebody else is sending on the same line, and some collision detection. Cool? All right, so that's a bit about what's going on here. The RGMIA, the receive interface requirement, allows a 1 nanosecond setup and 1 nanosecond hold. This is met, but only just so constraints are relaxed. So this is saying something about that stuff. I don't know, negative 1.5, if that's the covering slightly more than the 1 nanosecond or what. But at any rate, that's what's going on there. All right, so those are constraints. BD, I'm going to guess, is the board. And this is the XML we looked at before. We've got a block diagram that's got a microblaze design. Something about being on the top. And it's got like this, the UART interface goes here, something about a bus interface. So this is describing, I guess, the layout of the board somehow. And I'm guessing that this is ultimately done in a GUI editor. And possibly looks like this, something like this, depending on your viewer, I'm going to guess. But I don't have a viewer. Okay. So that tells me what BD is and all that stuff. MSIM is maybe simulation. There's something about testing. vlogsim, vlogsynth.f. I don't know what .f is, but these are just like lists of, this is just a list of files. Wave.do, on error, wave activate next pane. Add wave, no update. So these are a bunch of maybe test cases. Configure wave, wave restore zoom. Maybe we can just look up some of these keywords to see just what like tool we're using. Wave, restore zoom. Model sim, Questasim. I'm guessing model sim is relevant. It's an HDL simulator. Simulates behavioral, RTL, and gate level code. Okay, so this is for simulating. This is like, we talked about this last week. This is a part of making a chip, is the simulation part. And now we are on to the other parts. We have RTL, TB, and TC. And how do we want to handle this? TC is test case. TB is maybe something about the board. I'm still curious about this timescale thing. And we've got some clock stuff, sys clock, also the Ethernet clock. This has some TCL, this tickle K thing. I don't know what it is. I don't know what a DUT is. Micro B top. I think that's the microblaze thing. DUT. I'm not sure, but we can look at the microblaze. We've got some LED stuff, some sysconnect stuff, UART. Here's the maybe physical layer, Phi RST. Here's the RGMII interface, and then whatever MDIO is. And the UART has some stuff, whatever RS-232 is. We have Phi reset, and I guess this is maybe like send the reset signal to the physical layer. RGMII has this transmit D, transmit control, transmit C, receive D, receive control. I don't know if that's from the, if those were in the Wikipedia entry. What? RGMII. I don't know. Transmitter signal. I don't know. Transmit data, I guess. Transmit data, transmit control. Transmit, what is C? Clock? Clear? Receive data, maybe receive control and receive C. And then whatever MDIO is. Management data input and output. And then a serial management interface. It's a serial bus defined for the Ethernet family of IEEE 802.3 standards for the media independent interface. Okay, so it has two signal interfaces, a data interface to the media, to the Ethernet MAC for sending and receiving Ethernet frames, and a PHY management interface, MDIO, used to read and write control and status registers of the PHY in order to configure each PHY before operation. Okay, so That's all good. And then what is the other one? The MDIO clock interface is the MDC part. So that's that stuff. We're slowly connecting some of the, to me, totally inscrutable Verilog code to the standards. Let's remind ourselves what system Verilog is. A blah, blah, blah. It's an extension of Verilog. What does it do? All features of that language are available. If for verification, it uses extensive object-oriented programming techniques and is more closely related to Java than Verilog. And they're generally not synthesizable. So it's commonly used to model, design, simulate, test, and implement electronic systems in the semiconductor industry. Let's ask Gemini, what's the relation between Verilog and system Verilog? So it adds stuff. It's backwards compatible. Is it right to think of SV as a successor to Verilog, or do they have different niches? Okay, so I'll think of it as a successor. Kind of like C++ versus C, possibly. Okay. And I just still don't know what DUT is. DUT, AMD. I don't know if DUT is a... is a chip thing or a device under test. Okay. So this is I think a testing thing. Maybe TB is test bench. And then that brings us to RTL. We have the microbial top, which is I think the top level bit of the chip that is from Microblaze, the AMD kind of CPU stuff. Hello. How's it going? And so we'll look at the EMAC. And now it looks like we're doing some interesting stuff. And let's also look at this. This has what? You've got some clock whiz, some example design clocks. This is the support folder. I'm going to guess that we can skip the support folder. Do you think that's okay? I hope so. So we have this component XML. Let's just verify. This is probably, again, just a layout thing. Looks similar to the other thing, except it's got an XML extension instead of whatever the previous one was, B something or other. SW, I'm going to guess, is software. I think we peeked at this before. So try mode EMAC. I don't know why they're calling it EMAC. It's going to confuse me with Emacs, the editor. But this is a C file, and we're going to do C-like stuff in here. We've got some physical addresses, physical ID 1 and 2, some variable for the link speed, a variable for the duplex, which is an int, although it's possibly being used as a bool. On startup, this is C, I know this. So this is something I can understand better. We're calling this XIL out 32. Presumably XIL is for C links. And we're passing into some stuff, some config management. These are like presumably flags. We're doing some bitwise stuff. And this is related to MDIO and clock divide. We're going to call this is update speed. We're calling again this Z-Link in 32. passing in the youth unsigned 32 TME Mac base plus speed config add. And if value is 0, then we'll do this computation with speed config add. Okay, so this seems like it's maybe doing. This seems like it's maybe doing algorithmically maybe algorithmically is not the right word. This seems like this is possibly the actual implementation of the behavior of the Ethernet standard, or at least physical to Mac layer. We have this comment: evaluation board features. On power up or on reset, the PHY layer is configured to operate in GMII mode. With this PHY address, 00111, using some settings from some table, they can be overwritten via software commands passed to the MDIO interface. Okay, so this is some software stuff. We've got a make file, and really it's just one thing: a header and a C file. And I see Marvell here. I thought Marvell was a different company. We've got a Marvell physical ID, physical model mask, I suppose. Receiver configuration. This is, I guess, a register address where you configure receiver stuff, maybe. Let's see what Marvell has to do with any of this. So Marvell Technology Group is an American company headquartered in Santa Clara, California. An annual revenue of $5.5 billion for the fiscal year 2024. And what, they have a stock ticker. Marvell Technology. How are you doing, Marvell? Well, everyone's down. January 17th, though. Is that DeepSeek? I'm trying to figure out when DeepSeek was announced. I can't spell anything today. In January 2025, they released this one. 21 January. Hey. 2025. So let's go back to Marvell. Yeah, this is about a few days after that, I guess. Or maybe, I don't know. Well, right around this time, I think is when DeepSeek was released. I think that's what's going on with that decline. Okay, so somehow Marvell is making chips, and they are... They IPO'd near the end of the dot-com bubble, poor guys. But they don't seem to be related to AMD or FPGA or Z-Links. So I'm not sure what Marvell is doing here. I'll say, what's going on with Marvell here? This is from an AMD/Z-Links FPGA for Ethernet. It doesn't seem to use any Marvell stuff that I see explicitly. I've hit upon a common scenario in embedded systems and FPGA development, the use of manufacturer-specific identifiers within code, even if there's no explicitly visible Marvell hardware on the FPGA. So a Marvell Ethernet PHY chip. So it's looking for a PHY with the vendor ID of this. The PHY chip is almost certainly an external component, not integrated. Okay. They're typically separate ICs that handle the physical layer. And the FPGA using the RGMI interface communicates with this external PHY. Okay, so I had assumed that the PHY chip was part of this design, but it seems like Gemini is inferring that it's not, which is totally fine. But we are going to communicate with it over the RGMI stuff. And we've got some more MDIO stuff. We've seen what that is. This is just the header. Here's a struct. Structs are always good. We've got a base address, MAC high and low, and an IP address. Okay. And then we've got some data stuff, including MDD, whatever this is, trigger, try mode, blah, 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 some options, and some tickle. And I have no idea what that's doing, but I don't care enough to look at it. So that's the software. Here's more, this is maybe the layout. After it's been laid out, we've got this on slave and on master stuff, which is that terminology is being phased out of the industry, but maybe it's still present in some places. This is also, I think, an older project. I don't know what Spirit is. So this is from Z-Links. And Spirit is Spirit Consortium. XML has a reputation for being terrible and outdated, but at least they tell me with URLs what's going on with their stuff. So here's something. This looks totally 90s. Let's see if we can find anything about the Spirit Consortium. It was created to develop a standard for more efficient integration of IP in system-on-a-chip's SoC platform design. Okay, so this is just, I mean, not just, that's an important thing, but that's for, that's a standard, they're using it. This is some GUI initialization, presumably for visualizing the layout or stuff. And now we can go into the source. We have common support in FIFO. And is this the main thing? 389. It's not a lot. We have speed control. Here's the RGMI interface. What is this? So how is this laid out? This is the support thing. Instantiate the tri-mode Ethernet MAC support level wrapper. This is a MAC receiver client, whatever I over F is. This is just describing the wires. We have, I guess, transmit data. This looks like 8 bits. And then 1 bit each for T valid, T last, T user. I don't know what the user bit is doing. Scrolling up, we have the FIFO block, which has a bunch of inputs, including the GTX clock, G transmit clock, maybe global transmit clock, a reset, which it says is asynchronous, receive AXI, I don't know what RSTN, reset something, and then a reference clock for I delay controls. They had something for receiver statistics, but I guess they commented it out. And then this receiver interface that has a FIFO clock, a FIFO reset N, some more. I don't know what axis is. I don't know what FIFO is first in, first out. Maybe FIFO clock just means that there's a FIFO queue, like a hardware-based queue, and it's the clock for it. And then these are maybe just queuing up these signals. So as the signals are coming in, I guess they're being changed from ones and zeros on the wire into bits or bytes or whatever it's doing, nibbles, and those go into the queue, I guess, and then whatever the receiver is going to read off the queue. I'm guessing is what's going on. I still don't know what axis light is, or axis. Let's look up axis light. I keep not typing that quickly. So there's an Ethernet subsystem. The AXI Ethernet subsystem provides a control interface to internal registers via a 32-bit AXI 4 light interface subset. This AXI 4 light slave interface supports a single beat read and write transfers. Supports single beat read and write transfers, no burst transfers. The transmit and receive data interface is via the AXI4 stream interface. I don't know. I guess this is some chip thing that AMD offers for Ethernet stuff. But let's see if I can figure out what it's doing. A control interface to internal registers. I don't know what that means. So I'm also seeing a bunch of Axis stuff. Each port of an Axis, this is a network switch thing. I don't know if that's related. And then the AXI is just returning the AMD. Let's ask Gemini about it. Let's ask ChatGPT about it. And let's use 4.0. Why not? It's an IP core for implementing Ethernet communication. And it uses this GMII stuff. So it seems like maybe we're mostly getting Ethernet possibly from this library. Is that right? Is that the right way to think about this? And we've got some more transmitter stuff and so on and so forth. And we've got a comment here, critical applications. They're not designed to be fail-safe, such as life support, okay? And here's some layout. This is the block level VHDL wrapper. I think we're in Verilog. Where's VHDL coming in? Is this VHDL? Maybe this isn't Verilog. Let's ask the AIs. I'll say, is this Verilog or VHDL? I'll ask, what's the VHDL file extension? .vhd. Okay. So it does seem to be Verilog. I don't know how VHDL comes into this picture. Enhances the standard Mac core with an example FIFO. The interface to this FIFO is designed to the AXI-S specification. Please refer to core documentation. So let's look at this. There's some ARM link is coming up. An AMBA. Okay, I think this is it. The AMBA stream specification. It seems to be related. This is some AM advanced microcontroller bus architecture specification for something about buses. And this needs additional citations. Okay, so this is some specification. And then we have, in the picture, we have some AXI stream coming in. And there's a FIFO block level wrapper. This is, I guess, just some system that we're supposed to think of as one object, but it's composed of sub-objects. And this is some Ethernet FIFO. And we have a transmit AXI FIFO. That's like the transmit queue, I guess. And then we have a receive queue. And the whatever I over F is, this is the tri-mode Ethernet max support level. I guess we're going to read off the queue, do some AXI stream stuff, possibly, although this is also AXI stream. And then you have some TX phi I over F stuff. Phi I over F. And what is this timescale? Okay. Let's find out what I over F is. And let's find out what the timescale is. So in what follows, what is I over F AXI, what is it, AXI dot S, and what's the time scale? So I over F is just interface, and it's the communication boundary, blah, blah, blah. AXIS FIFO is transmit and receive in the tri-mode Ethernet MAC. It's essentially a set of signals and protocols that allow these blocks to exchange data. It's a member of the ARM Advanced Microcontroller Bus Architecture protocol family. It's designed specifically for streaming data. It has a unidirectional data flow. It's got some handshake. And it's simple. And the time thing means that the time unit is a picosecond. This is the base unit. And the time precision is a picosecond. This is the accuracy with which time delays can be represented. Okay. So what would... I guess that means the... Nanosecond is the time unit and picosecond is the time precision. Okay. All right, so this is kind of getting to some of the stuff. Support, here's the support layer thing. You've got a receiver interface and a transmitter interface, and we've got a statistics vector, which is pretty large, and everything else. So the data is like, what, 8 bits wide? I assume this is a bit. I don't know what this delay is. Maybe it contains like something like a timing information. Here's the Mac control interface. We can pause request, maybe. We request pause. We can pause val. And we've got like, I guess 2 bits for what the speed is. And then we have this RGMII interface. And it seems like this is all about laying out the chip connections. And it's possible that mostly the actual Ethernet behavior is implemented in the software, possibly. But I don't know. It seems like we're handing off a lot of the design to the external chip, the physical layer chip, which seems to be from Marvell, and the AMD Ethernet subsystem chip, whose name I've forgotten already. This is just some clock stuff. I have to go in a little bit. We'll look at common. Here's a sync block. I don't know what a sync block is. Async reg true, shreg extract no. We got clock data in. I don't know what this different syntax is. This is more wiring stuff. This seems like it's possibly behaviory stuff. Don't touch equals yes. Okay, I assume that's for tooling and not people. Here's a reset sync thing. This is, I guess, there's some async stuff, and I'm guessing that maybe these sync files are for when you once you asynchronously request some stuff, something has to make sure that it happens. I'm guessing that's what the sync stuff is. It's somehow synchronizing. And then here's some FIFO stuff. I don't know what BRAM TDP is. Tri-mode Ethernet MAC BRAM. Some kind of RAM, block RAM. We've got port A and port B. We've got some shared memory. Local param RAM depth is 2. To write, use port A. To read, use port B. But how do we say that it's RAM? We have this mem keyword. Are we importing something? All right, I'll say here, where does the keyword mem come from? Is it a variable defined in the code? Or is this some something else does, and what? So what makes this RAM as opposed to a bunch of wires? So there should be something about gates, right, that store information. It's part of the Verilog syntax for declaring a memory array, a RAM. It is declared here. Okay. So this defines each element of the memory array as a register, blah, blah, blah. Therefore, mem is variable, but it's a special kind of variable. The reg, so I guess register is a thing that holds, it's a bunch of registers is perhaps the way to think about it. Creates a storage structure. Okay. So what is what's a register in Verilog? I'll ask what kind of gates are involved. I don't know if it's just like a bunch of like flip-flops or something. Okay, so reg just is like a keyword that declares variables. It does say not necessarily a flip-flop, which I did not ask about explicitly. So hardware registers are flip-flops. And then there's clock behavior, blah, blah, blah. There's a D flip-flop implementation. Various combinations of basic logic gates such as NAND gates, NOR gates, inverters. A common implementation uses a master-slave configuration with latches, which are themselves constructed from logic gates. Okay. All right, and I have less than a minute left, but I do want to at least look at the FIFO. Do I want to look at this one? Or another one? This is now pretty long. So we have Mac last valid user, FIFO status, FIFO overflow. And this should just be like it should look a little bit like a queue, but like a hardware version. A clock, reset N, FIFO T data, 8 bits. Status, overflow, etc. We'll come back to this. Let's look at the, I guess, transmit one. Okay, so we get some state machine stuff like idle, some queuing. We're waiting for a handshake. I guess there's like maybe we're what are we transmitting a frame, or we have a frame. Handshake, I guess, finish, drop errors, drops, retransmit errors. So this is looking more like the Ethernet protocol. We've got registers for the wire state, wire next state, wire EOF data BRAM, and a data pipe. Something indicating that FIFO is full. An address, I'm guessing maybe a MAC address. How many bits is a MAC address? 48 bits. I don't think this is big enough to hold a MAC address. Okay, so this is starting to look more behaviory. This seems to be like maybe the heart of the work that went into this. But I believe this is just the FIFO queue. So here's the beginning of the FIFO architecture. Write state machine and control. States are wait, data, end of file, I guess, or overflow. End of F, FIFO. Decode next state, combinatorial. So we're going to, I'm guessing these are like the inputs, like the wire inputs. And we're going to do a case analysis. If we're at the beginning, we're going to, I guess, look at some pipe stuff and some end of pipe stuff and so on. If we're receiving data, we'll wait for the next frame to be detected. I guess that's what this is doing. And I'm not really sure. So maybe detecting overflows, detecting into files, and then something about the next state. End of frame probably. If the start of the frame is already in the pipe, a back-to-back frame transmission has occurred, move straight to the frame state. Okay. Then we have some frame count, decode output signals. All right. Here's a read state machine. We have things like idle, Q2, Q3, QAC, frame, handshake, etc. All right, I do have to go. But I am curious how this implements a queue. How does this implement a queue, or is the actual queue implemented somewhere else? Let's see what it says. So it uses a dual port block RAM and state machines. Here's how it works. So the dual port block RAM, it means that it can be written to and read from simultaneously, which is essential for a FIFO queue. BRAM is used to store the data that is being queued. Okay, so that's what the RAM is for. Makes sense. The write state machine controls writing of data to the BRAM. It handles the following states, waits for the start of a new frame. Data S writes data into the BRAM. EOF handles the end of the frame. And then there's the overflow conditions. The read state machine controls the reading of data and handles some states. Address management, WR adder, and RD adder signals are used to keep track of the write and read positions in the BRAM. So these are not MAC addresses. These are addresses in the RAM. They're incremented as data is written and so on. And it uses the AXI stream protocol for both the write and read interfaces. Okay, so the AXI stream stuff is used for, like internally, I guess, is for writing to the queue, is what this is saying. T-valid, T-ready, and T-last are used to manage the flow of data. And the combination of BRAM, state machine, etc. are used to implement it. Let's see if we can see something about this BRAM. So the data S, we're checking for overflow and end of pipe and state. So this is writing to next state. I'm not really sure where it's actually writing to the BRAM. Do they tell us something about BRAM in this file? The FIFO memory size can be increased by expanding the RD adder, blah, blah, blah. WR data BRAM. Okay, so maybe this is like writing something. At any rate, I gotta go. So that's all for now. As a look at some FPGA Ethernet implementation, I understood very little of what was going on, but I feel like I now know much more than I used to.